Hi. Okay, so go team. You've gotten through the focus 1, ideal gas law, focus 2, internal energy and enthalpy, and then focus 3, introducing entropy. I kind of want to bring it all back together. This would be one of those, it's not a specific set of notes that I would share. This is just conversations we would have throughout the course. And so let me get on my soapbox about the laws of thermo. All right, so the first one, I should say the zeroth law of thermodynamics. This defines temperature. The idea is if A and B and C, so if A and B are in thermal equilibrium and B and C are in thermal equilibrium, that means A and C are in thermal equilibrium. And like I said before, that's a dumb definition because what it means is when they are not in equilibrium, heat flows from hot to cold. And it's in that flow, that spontaneous transmission of heat energy, that you then get the second law. But before we get there, let's go with the first. And so we've got U is equal to Q plus W. And so there is a state function that exists such that two state functions added together on any process will equal their internal energy, which is a state function. So not state functions equals state function. That is hard to think about. And if you're like, okay, yeah, that makes sense, you're not doing it right. Really think about what it means to be a not state function equal to a state function. Go team. Second law. So we've got delta S of the universe is always increasing. Or you have no process is possible in which the heat, Q, which spontaneously goes from hot to cold, zeroth law, can be 100% converted into work. So this is not possible. There has to be some small amount, some heat has to flow. Actually, so some heat can't not be converted into work. And in all honesty, most of it can't be converted into work. 99, well, not 99%, 33% is the ideal efficiency of a Carnot engine. And that's an ideal engine. Engines are not efficient at all. There's so many students who are like, well, it's not 100% efficient, so I wouldn't invest in that engine. It's like 100% is not possible. We're good if we're doing 25. Okay, so that's the second law. No process can occur spontaneously. Heat goes from hot to cold, and all of the heat be converted into work. Then we get into third law. S equals 0 at 0K. So this means S is equal to K log omega, where this is what's called the number of microstates. Sorry, I should make that bolder. So this is the number of states. And here we've got Boltzmann's constant, which is the energy per Kelvin. Okay, so this is joules per Kelvin. Now, if I were to convert this to molar joules per Kelvin, so convert Boltzmann's constant to moles, instead of per particle, if it would be per mole of substance, then I would have the gas constant. And so third law says that the entropy of a perfect crystalline solid at 0 Kelvin is 0. This defines our 0 Kelvin. So we've got a kind of a bookend. We have a definition of temperature through the zeroth law, but then we have a definition of the absolute zero, so where we're starting from for the third law. And then the second law tells us that it will always be increasing, this change in the entropy. And then first law really tells us the constraints on the system of like where the energy can go. It can only be converted between heat and work, and that's going to be contained within the internal energy. What you do with that afterwards, it could be that there's an expansion in addition to the internal energy. So then you'll have an enthalpy. Well, can you convert that into non-useful PV work? Yes, you can. That's the Gibbs energy. Okay, so let's dive deeper into that. Yeah, I'll do, okay. I got to think about what I want to talk about. Okay, so zeroth first, second, third. And if you ask me, Allison, do I need to know all the different ones, like zeroth, which one's second, which one's third? Yes, you do. Yes, it is very helpful to know all the differences, especially the second. Second is so important. Okay, so delta H is equal to delta H, or delta G is equal to delta H minus T delta S. What does this mean? For my biochemists in the room, you've seen this a gazillion times. For my chemists in the room, you've seen this a gazillion times. I want you to think about what this function says. Okay. Not all energies are created equal. Let's look at units. Again, you can do all of pChem with a unit analysis. Joules, and we're just going to assume 1 mole of my system. That way I don't have to carry the moles. Joules is equal to joules minus Kelvin, joules per Kelvin. First of all, I'd like you to think of the quantity, or not the quantity, the magnitude of these things. Typically, delta G is what order of magnitude? Typically, delta H is what order of magnitude? And typically, delta S times T is what order of magnitude? In your comments for your homework, you should be finding this out. You should be exploring this. So these two are typically, for a chemical reaction, they're going to be about 1,000-ish or so kilojoules. This is normally in the hundreds of joules. So this one's always smaller. Does that make sense that it should be? Why? Okay, so I want you to define for me, and normally we would be doing this in a group. Kind of hard to do that because this lecture is so important that I want to have it recorded for you so you can go back and rewatch it. But I want you to figure out what each of these represent. Okay, so non-expansion work or non-PV work. Okay, this is work energy. Or sorry, oh my gosh, sorry. This is heat energy. And this is minus the entropy term. And I say entropy term because you've got both the entropy multiplied by the temperature, so it converts it to an energy. Okay, there is no process in which the sole result is the complete conversion of heat into work. The second law says this cannot be zero. This is actually an embodiment of the second law. It's kind of beautiful, as is so many other things. The Chatelier's principle, second law. Everything is second law. It's lovely. Okay, anyway, so there is no process in which the sole conversion of heat can be made into work. So that means that there has to be some amount of heat energy lost that cannot be restored, that cannot be converted from heat into work. And that is your entropy term. So what does that mean? Well, S is equal to K log W. And let's turn that into the per mole. So S molar is equal to R log W. That's fine. So when you multiply, so what is R? So if you want to know how much energy you have per unit Kelvin that you're in, if you think of this almost like quanta, but not really. It's not really packets of energy because this is bulk macroscopic thermodynamics, and so we're not looking at quantized energy states. But there are certain number of energy units that can be present per degree Kelvin per the number of states possible. Entropy. So when you count this, if this is the number 7, then you have 7 Boltzmann's constants, or 7 R's, all multiplied together, all right? And so what this does is this tells you, for your particular change in your system, the number of possible states that are going to be changing based on the thermal energy that you have in the system. Okay, so based on that, you're going to have then a metric for how much of a change in your number of states are possible. Another way to think about this is how many, well, again, how many R's that you can have, but how much energy are you going to lose as you create those new states? So one of the things about entropy is always increasing, a lot of students are like, oh yeah, that makes sense, entropy is always increasing. Why? Why would entropy always be increasing? If entropy is the number of possible states present, does it make sense that it should be? So what I want you to think about is, what does entropy represent, and how is it different than an energy? And then how is it different than a specific energy? Internal energy, enthalpy, Gibbs free energy, Helmholtz energy. So you got 4 different energies to choose from. And you can ask yourself, again, every one of these thermodynamic potentials, so A, delta A is equal to delta U minus T delta S. So there's going to be a change in entropy multiplied by temperature. This makes it an energy that you cannot get converted from the internal energy into the work energy, which is the Helmholtz energy. Okay, you're going to lose some along the way. Okay, I think that's all I want to say for now. Okay, the last thing I want to talk about is heat and work. Specifically, we started this class a couple weeks ago looking at PV equals nRT, and we will continue to look at PV equals nRT. Think about what this represents. So what if I said, okay, well, what is delta PV is equal to delta nRT? What if I said delta PV minus, and I'm going to say that N is constant. Does this look familiar at all? RT. You see RT, you should think thermal energy. RT, thermal energy. Joules per Kelvin multiplied by Kelvin gives you an energy. So by multiplying R by temperature, what you're doing is you're converting temperature into its energy units via the Boltzmann's constant. But that is thermal energy, which is heat. PV is work. Work plus heat equals 0 for an isolated system. This is your first law of thermo, hidden within PV equals nRT. This is why I get so mad when people are like, it's PivNert. I'm like, it's so much more than PivNert. It is the first law of thermodynamics. It is the fundamental equation of state that we can use to understand the thermodynamic potentials. It is so much more than PivNert. Anyway, okay. Cool, but what's the take-home message? You should be able to identify the differences between those two things by looking at the mathematics. And you should be able to tell me what is G, A, U, H, and S. And I'm going to say S, well, yeah. Really should be ST, but that's okay. All of these thermodynamic potentials have their unique definitions. You would never use Helmholtz if you're wanting to talk about batteries. Absolutely not. Why? That's my question to you. When are you going to use all of those? And can you relate those thermodynamic potentials to the heat and the work definitions? Go team? Awesome. Okay, cool. Sorry this isn't a video. I would normally, this would just be a chat that we would have. But I want to make sure that everyone's involved with the chats. So it's a video now. Yay. Go team. Okay, hope you liked it. This stuff is so freaking cool. Literally thermodynamics. Okay, I'll stop. Send me questions.